Problem B5. Charlie chooses one cell from a blank n by n square grid and shades it. The resulting grid has no lines of symmetry. In terms of n, how many different cells could be shaded? Now, let's find the pattern in the shading. However, I'm going to shade cells that have lines of symmetry when shaded. And then we can subtract it off n squared, which is just a number of squares, to get the resulting. Okay, so you can observe what happens as I color these. These are the ones when I color, they have lines of symmetry in them. I'm gonna be quiet and you can start observing. Okay, now after observing, you might have noticed different things, but the main point was to identify that the most important squares are these two, as they go as the centers of different squares, grids, right? So for n is even, what do we have? When n is even, we find that we have the central bit of the square is 2 squared, which is 4. And then you add on n minus 2 over 2. 4's, well, it's a bit hard to explain, but I will explain now. As you can see, for the 6 by 6, you have the center 2, which is 4 squares, as I've added just now. Now what we can do here is see that we have 4 layers left, right? And each pair of layers contains 4. So then we add n minus 2, which is 4 layers left, divided by 2, which is how many pairs of layers there are, and each pair has 4 squares that can be colored, right? Now we just have to simplify to get, well, let's see. 2n minus 4 plus 4 is equal to 2n, right? And therefore, we just found when n is even, the number of squares that can be colored so that it has lines of symmetry is 2n. However, we need to do n squared minus 2n, like that, because we're finding the ones without lines of symmetry. Indeed, right? Okay. Next, n is odd. We have observed earlier there is a center of 3 by 3, which is 9. So we have 9 plus, what do we have here? For every pair of layers, like this, which includes, well, for every pair of ring around the center, there is 8 extra. So we can do a similar thing. N minus 3 this time, because it's 3 squared, over 2 still, multiplied by 8. N minus 3 is just how much left there are. 5 minus 3 is 2, there are 2 left. 2 divided by 2 is 1 times 8 is the extra 8 we have, so plus the 9, right? So now we can simplify. Peaceful music in the background, if you have noticed. If not, well, I don't know why you cannot hear, but we just rearrange. Sorry, I did a mistake. And that simplifies to that. So what we have to do now is to subtract n squared off that. So n squared minus 4n minus 3, like that. But then if you remove the brackets, that becomes a plus. So it is indeed weirdly a quadratic, right? But of course we don't have to factorize, guys. Do not factorize. You don't need to in this exam, in the JMO. You just need to state that. Now, what can we do? Well, I said I'm going to generalize. Wait, did I? Maybe. Okay, but this is a piecewise definition of our colorings. This is allowed in the exam, but what if we wanted to generalize? Just a bit of extra practice with modular arithmetic. Really, you just have to do when n is even, right? So we want this to be multiplied by 1 when n is even. So we can multiply this whole expression by n plus 1 mod 2. Then add that expression to the odd bit. So if it's odd, we want it to multiply by 1. That's kind of easy. So we have n squared minus 4n plus 3, all of that in here, multiplied by n mod 2. Like that. So that is our generalized formula using mods. And that is our final answer. And that is also